Hi everybody, in this video we're going to go quickly through a couple of examples on how to graph motion. So we've been talking about things like distance and velocity and time and acceleration. So let's talk a little bit about each of those a little bit more in depth. So first of all, the equation for the slope of the line. We all know the equation, I hope, is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And another way we can say that is delta y over delta x. And that delta, that's the letter delta, a Greek letter, and it means change in. And so when we say delta y over delta x, we're talking about the change in x, or excuse me, the change in y over the change in x. And so when we talk about velocity, we're talking about the change in distance over change in time. And we talk about acceleration, we're talking about the change in velocity over change in time. And we've talked a little bit how we talk in distance, we measure distance in meters, and we measure time in seconds. And so velocity is measured in meters per second. Velocity is measured in meters per second, and time is measured in seconds. And so acceleration is measured in meters per second, or meters per second squared. And so all those units go back to the basic definitions. These definitions are not on your AP sheet. You do need to memorize those. A lot of you, I think, already know them, but you do need to memorize those formulas. Those are not given to you. Now, if we go down to the example, what we're going to spend some time here is going sort of back and forth between a displacement time graph and a velocity time graph. Before we do that, let's just take a minute to read through this little paragraph. The slope of a line on a curve of displacement versus time is equal to the instantaneous velocity at that particular time. And we've talked about that, how slope of a distance time graph will give us velocity. In a similar manner, the slope of a line or a curve on a velocity time graph is equal to the instantaneous acceleration at that particular time. We haven't talked a whole lot about that, but we will. We'll keep going and giving some examples of that. So for this example, what I want to do is go through how to change a displacement time graph, so this was displacement time, into a velocity time graph. And so to do this, I'm going to break up this graph into a couple different parts. And I'm just going to say this is part 1, this is part 2. I'm going to call this whole thing part 3, and then this will be part 4, and this will be part 5. I could have called it A, B, C, D, whatever, but I'm just calling it this. Now, if we look at this graph, we ought to be able to tell what's going on here. And so in this case, the steeper the slope is, the faster the acceleration, the faster velocity is. So this is maybe a walking or a fast walking, but then this is much steeper, and so they're walking much faster or maybe running in this section. And the places where they are horizontal there, they are stopped. And also the direction matters. So this has a positive slope, so it's walking or running in the positive direction. This one has a negative slope, so it's running backwards past where they started and towards another point. And then they stop there for a second, and then they go back the other way. Okay, so we need to analyze each one of these. So we're going to start with section number 1, and we are going to find the velocity of that section. And the velocity, of course, is the change in distance over change in time. And we can do that by subtracting, or we can just do it by counting squares. But if I go from here to here in this first section, I'm going to say that it goes up 20 and over, we have to figure out our units. What's our unit here? Here's 20, so what about 5, 10, 15, 20? Yeah, so this is 5 tenths. This is 10 seconds, or 10 seconds. I'm going to write that on there just because we need to know it. So that's 10 seconds, that's 20 seconds, this is 30 seconds, and so forth. Okay, so for this, if it's a person, if it's a car, or whatever, the velocity here is 20 meters, or our distance is 20, and our time is 10 seconds. And so that is 2 meters per second, because 20 divided by 10 is 2, meters divided by seconds is meters per second. So that section is 20 meters per second. The next section, section 2, well, in that section, the velocity, the change in distance is 0, and the change in time is 5 seconds. So that's just 0 meters per second. Remember that if they're flat, they're stopped, so that makes sense. Section number 3, and you can do it, let's just do it for the whole thing. So it goes from 20 down to -20, so that's actually a total of 40, isn't it? And the time span for that is 510 seconds. So this time they're going 4 meters per second. Section number 4 is also 0 meters per second. So if I want to write that down, I can. Seems like it's pretty obvious, but let's just go ahead and write it down. And then section number 5, oh, you know what? Let's make a little bit of a difference. Let's talk about positive and negative signs. So on section number 1, that was a positive slope, right? It's in the positive direction. Section number 2 is 0. Section number 3, though, isn't that in a negative slope? So that's a negative 4 meters per second. They're going back 4 meters per second. And then for this last one, goes from -20 all the way up to 0. So that's a change in 20 meters over 5 seconds. And that comes out to be 4 meters per second again. And that time it is a positive 4 meters per second. This one was a negative 4 meters per second. This one is a positive 4 meters per second. Okay, now that we have all 5 of our sections, what we want to do now is put these 5 sections onto this graph. And notice that the time axis is the same, and it will be. So we have 0, 20, and 40 here. Now, my y-axis might be different. In fact, I might want to zoom in a little bit because I only need to go up to 4. I'm going to change my y-axis. I'm going to change this to 8. So this one's 4. If we need to go to 5, there's my 5. This one is a -4. And if we need to go to -5, there's my -5. Okay, so each box is 1 meter per second. And I need to change this. This velocity should be meters per second. That's a mistake as well. Okay, section 1. In our first graph, section 1 goes for 10 seconds. So it's going to go from here to here. And section 1 is a positive 2 meters per second. 1, 2 goes from here to here, 2 meters per second. Section number 2 is 0 meters per second. So it's going to jump down here, and it's only for actually it is for 10. Oh, sorry, up here it's only for 5. So we're going to go right here. Section 3 is -4 meters per second, and it is for 10 seconds this time. So it's going to go from here to here at -4. And section 4 is 0, and that is for just the 5 seconds there. So this is going to be 0. And this is a +4, so I'm going to come all the way up here and go here. And then my time here is the end of the time here. Let me show you a couple things in case you're just not really sure what's going on, because there was a lot going on there. One thing is, notice that this section of 10 seconds is represented by this line of 10 seconds. Then we have this section for 5 seconds, and I have this section for 5 seconds. And then I have this section for 10 seconds, and I have this section for 10 seconds. And I have this section for 5 seconds. I have this for 5 seconds. And the last section is also 5 seconds. And this section is 5 seconds. Okay, so I want to draw those parallels so you see the time is matching up from this graph down to this graph. They match up together time-wise. Another thing is that I want to connect these, and sometimes people get a little stuck on how I'm connecting these. So let me erase some of my highlights and come back and talk about connecting. Okay, when I connect these, I'm essentially going to use a vertical line, but I know, and we all know, that if I did that, it would not be a function. And so some people like to, instead of making it a perfectly vertical line, they kind of like to go like that a little bit, where it's not exactly vertical. And that makes sense. And so we can do that. And so again, I'm going to connect these, but again, not at a perfectly straight line, because we have to have some kind of acceleration there. And I'm just going to do that to each of these. I'm going to connect these lines, not quite vertical, but almost. And so something like that. And so just understand that when I'm connecting these, I really, vertical is probably a little bit more accurate, but we have that difficulty with not being a function, and you can't be in two places at once and so forth. And so we're just going to connect it a little bit off of the vertical. Okay, this graph is a displacement time graph, and the bottom graph is a velocity time graph. They are saying the exact same thing. That is, I've been sticking with walking. So this could be, for instance, walking. This is stopped. This is maybe running a little bit faster. And then this is running back the other way. So that same thing is going on here. This is a velocity time graph. And so it's a little bit different because it's velocity time. But here we are running at a constant velocity. And then we stop for 5 seconds. And then we run a little bit, then we transition over. And then we run a little bit faster, but we're running backwards. So it's a -4. And then we transition and we stop for a second or 5 seconds. And then we transition and then we run the same speed as we were running here, except we're running forwards now. Here we were running backwards because it's down the negatives. Here we're running forward because it's in the positive direction. Okay, we will spend some time changing between displacement and velocity, and then we have one more layer to go, and that's from velocity to acceleration.